Yeah, I think recording has started. Okay. Good morning once again to all of you. So in the last class, we were discussing about the small signal equivalent circuit of this MOSFET. It is an N-channel MOSFET that we have seen, right? So N-channel MOSFET, sometimes we also write it as NMOS or N-channel MOSFET, right? And this is a symbol of that. And we have seen from here that the small signal equivalent circuit would look something like this. This is gate. Right. Small signal equivalent circuit would look something like this. This is gate, this is drain, this is source, right? And between gate and source, we have VGS, and here we have a current source, which is GM VGS, right? This is for the case where the current characteristics or the ID VDS characteristics is expected to be like this. They are actually in parallel of this VDS axis. However, for practical MOSFET, we as discussed in the last class, we know that the characteristics would not be this parallel to this VDS axis, but it would have some positive slope, right? And this is due to the channel length modulation, because of this slope, they are in small signal equivalent circuit like BJT. Another resistance will also appear, and that resistance we have extracted, or we have calculated from here. We have written the ID equation like this, right, to represent that channel length modulation effect. Then from here we have find the value or expression of this R naught, which comes out to be 1 by lambda IDQ. And from here we have seen that the overall characteristics, including the channel length modulation effect, you have to include this R naught here, right? So that's all, okay, for N-channel MOSFET. However, what will be the case or small signal equivalent circuit for P-channel MOSFET? So for P-channel MOSFET, the symbol is like this, right? Circuit symbol, source, gate, drain, and we know that compared to this NMOS, we have some difference in the nomenclature. For example, we in NMOS we generally say V of SD, drain to source voltage, because drain will be at higher potential. But for PMOS or P-channel MOSFET, as the source is the higher potential compared to the drain, so we will say it as V of SD. Similar, in the same token, we can also note that unlike N-channel MOSFET, here we have to say V of HG, right? So these are the difference. So, as you can correlate also this thing with that we have already studied for bipolar junction transistor. And from here, we can also easily draw the small signal equivalent circuit of this P-channel MOSFET. So here also, so this is basically gate, and the other terminal is this source, right? And here we know that this is at the higher potential source, so it would be this V of SG, right? And then the direction of this dependent current source will also change here. It would be V of SG, right? And here we will have this R naught, right? So this is basically the small signal equivalent circuit of this P channel MOSFET, right? So if you can find what is the gain for NMOS, so you should be also find what is the small signal gain using for a circuit which uses this P channel MOSFET or PMOS. Right? So it should be quite straightforward. But in this particular our lectures, we will primarily focus on this NMOS, right? But I request you to please also do an extensive study for this for circuit consisting with P channel MOSFET as well. Right. So again, let us then come back to this N-channel MOSFET once again, and let us do one example and see how to find the small signal equivalent or small signal gain for this particular amplifier. So, so you can clearly see that this configuration is the common source or CS configuration, because source is common, right, between this input and output, and output has been taken from the drain terminal. Right. So here this Vi is the input signal, which is which is fed through an input resistance of Ri, coupling capacitors CC1, CC2, and source is grounded here. No resistance present. Here is the drain resistance, and this is VDD. Right. And the corresponding values for this VDD, these voltage sources, as well as these resistances are also given. For example, VDD is given as 10 volt. R1 given as this kilo ohm, R2 29.1 kilo ohm, RD value, threshold voltage of this MOSFET is given, Kn value given, lambda, that is a channel length modulation parameter, that is also given, this Ri value is also given. Now I have to find the small signal gain, right? Then what should be the first step? Like we have done for BJT, right? First we have to do the DC analysis, right? You have to do the DC analysis and you have to find the Q point, because until and unless we know the Q point, we cannot find what will be the small signal, small signal equivalent, the values of the small signal equivalent parameters, right? For example, GS, or what will be the value of this R naught, that we cannot find until and unless we know the parameters, or this DC parameters, right? For example, we need IDQ. We need IDQ to find the value of both GM as well as this R naught, right? So let us first do the DC analysis, and we know that during DC analysis all capacitors would be open circuit. So that way, for DC analysis or for DC part, this part is neglected. Similarly, this part is also neglected because these are open circuit, right? So you have only this part, right? Only the middle part of this. So let us now focus on this. So how to start with that? We have to first find what is this VGSQ. That is this point, VGSQ, this plus minus, right? So that can be quite straightforward. We can find out, like it would be VDD into this R2 divided by R1 plus R2, right? So see, all the values are given here. So I request you to check the value, and for time check, I am doing it. I am writing the value, but I request you to please do this thing or cross check these values once again. So if you calculate it, it should come around 2.91 volt. So this is 2.91 volt, and the threshold voltage is given as 1.5 volt. So obviously VGSQ is more than threshold, more than the threshold voltage. So we can say then the transistor is on, right? But if the transistor is on, it might be in the linear region, or it might be in the it might be in this triode region, or it might be in the saturation region, right? So for that, we know how to approach. For that, we will assume MOSFET is in saturation, and when we assume this, we can write IDQ would be equal to Kn into VGSQ minus VTN the square, right? We can write this. Okay. Now, when we write this, we have to see all the values are now given. VGSQ value we know, VTN value is given here, Kn value is given here. So we know all the values, so we can find what is the value, what should be the value of this IDQ. And if you calculate it, it will come as 1 milliamps. So 1 milliamps is the current that is flowing through this RD, right? Okay. Now from here, then we can also find what would be the value of this VDSQ. Okay. So we can find VDSQ. What should be the value? So VDSQ would be equal to this VDD minus ID RD, right? From this, you take a loop, KVL along this loop, right? From VDD to ground. Right? So it become then you have to, the VDD value is given, ID, everything is known from here. So if you calculate it, it will come as 5 volt, right? So this is VDSQ, right? And what is VDS saturation? VDS saturation for this transistor would be VGSQ minus VTN. VGSQ was 2.5, no, 2.91, right? And this is 1.5 threshold voltage. So this would be how much? 1.41 volt, right? So obviously then VDSQ is higher than this VDS sat, right? So the transistor is in saturation. Right? So the transistor is in saturation. So whatever our assumption was, that is correct. So now once the transistor is in saturation, so you can proceed, because until and unless it is proven that the transistor is saturation, we cannot draw this. We cannot draw this small signal equivalent circuit, right? So yeah, so the transistor is in saturation. Then we have to do the next part would be the AC analysis part, right? So for that, let us go to the next page. Let us do the AC analysis here. So now we are doing the AC analysis, right? So for AC analysis, we know that this all these voltage sources, VDD and everything, they would be grounded, right? This would be grounded. This capacitor would be shorted, right? This capacitor would be shorted, right? So this will be the AC equivalent circuit, right? Now, if you have to draw the total small signal equivalent circuit, then it is not difficult. So let us start from here. We have this small signal source. This is Vi, through which this Ri is being connected, right? Then you know that R1, R2 come in parallel, right? Because both are having connected with this ground, another terminal, right? And this is basically the gate terminal, right? And here it would be GM VGS, where this is VGS and this is the source terminal, and the source terminal is grounded, right? And with this is the drain terminal. With this drain, we have one resistance as well, which is R naught, right? Now, right? Now this is this RD, this is the drain terminal, and one terminal is connected with the drain, other terminal is grounded. So we can also draw this RD here, or right, RD here, right? So this is the small signal equivalent circuit, okay, of this amplifier. Now it is quite straightforward to find the gain. So here is this output, right? This plus, this minus, right? This is the output. Now we have to find. So gain means basically equal to, we have to find what is V output by V input. That is the thing we have to find. Okay. So for that, let us again focus on this, and let us try to find what is this VGS. What is this VGS? So VGS is, you see, we can use the voltage division and write VGS like this. R1 parallel R1 parallel R2, R1 parallel R2 plus Ri, right? Okay. And what is then okay? Then what will be the value or expression of this V output? This output is, see, these two resistances are in parallel, and this much current, GM current is flowing through it. So V output can be easily written as minus sign, because if the current flows, then this would be positive, this would be negative. So it is minus R naught parallel with RD into GM isn't it? Right. Now see, VGS we have already expressed in terms of VI in here. So let us replace that. So it is R naught parallel RD into GM. VGS we are writing as VI into R1 parallel R2 by R1 parallel R2 plus RI. Right? Okay. Now to find the gain, we have to do this V output versus V input. Right? So if we do that, it is GM into RD parallel R naught into R1 parallel R2 by RI plus RI plus R1 parallel R2. I hope I have not missed any term here. Right. Okay. Now see, what is GM? Okay. Now GM we can easily find from this expression. 2kn VGSQ minus VTN, right? This is one expression, and the other expression you know that is using the current I, right? So you can use any expression for to find this GM, either of these two, right? So if you calculate it, it will come as, because now here if it, all the values you know, 1.41 milliamps per volt. Okay, here R naught is also there. Now what is R naught? R naught is 1 by lambda ID. So, or IDQ. So you know IDQ, you know that the lambda value is given. If you find it, it would come as 100 kilo ohm. So you see now in this expression, if all the terms you know, right? Now substitute all the terms, the values here, right? And you will be able to find the numerical value of this gain. So that if you calculate it, the gain will come out as minus 5.62. And remember, for this common source, as already we have discussed earlier, that like CE amplifier, right? There will be 180-degree phase shift between the input and output. So the means the output would be out of phase compared to that of input, right? So this is not difficult, quite a straightforward calculation, and to find what would be the value of the small signal gain for any circuit using MOSFET. Right. Now, suppose if this R naught is infinite. Okay, see R naught is infinite, so that means the transistor characteristics is the ID VD characteristics is like this. ID VDS characteristics is like this. Right? This will be almost parallel. When it is almost parallel to this VDS, or the slope is very small, then R naught would be infinite. Right. Okay. So if this R naught is infinite, so in that case, if you look from this expression, this gain expression, then the gain expression would be, so this R naught is infinite. So anything in parallel with means this is a heavy high resistance and this is RD. So what would happen ultimately? It would become GM RD R1 parallel R2 by R1 parallel R2 plus RI, right? Okay. Now, if you just numerically means try to find like which one would be higher. So from this you can see this term is same, this term part is also same. Only difference is here this, and whenever you do any parallel with any value, then obviously like this parallel combination will have some lower value, right? Then if this R naught is infinite, then this gain is expected to be higher. Now, as this R naught value would decrease, so you can obviously see from here, your small signal equivalent gain is also expected to reduce, right? I hope there should not be any confusion so far, because it is quite straightforward and almost quite similar to that of our analysis of the CE amplifier. Right. Now here is the CE amplifier. Here is this again the CS amplifier, common source amplifier. But here what we have done, we have introduced one source resistance, right? Because we have during DC biasing only we have seen that we need a resistance here to get a negative feedback, right? To stabilize the circuit operation. So we have introduced this RS, and the remaining things are same like our previous discussion. So here we are not taking the numerical values. Here we just want to derive what would be the expression of this small signal gain if you introduce this RS or source resistance, and we will try to compare this value of gain or the from this these two expression, means the gain expression of CS amplified with source resistance and CS amplified without source resistance, and try to compare the magnitude of gain between these two, okay, from the expression itself. So to find the small signal gain, so it is quite obvious that we should draw the small signal equivalent circuit first. Okay, so here let us do that. So we have this Vi, other part is grounded. Here we have this Ri, right? And this would be shorted, to know that. So I am not, this would be shorted. and this would be grounded, right, for AC. Okay. Now this is R1, R1, R2 would be in parallel, like as per our discussion earlier. So it is R1 parallel R2, right? Okay. And this is connected with the gate terminal. So this is connected with the gate terminal. Between gate and drain, there is no direct that way connection. We know that, right? So here we know the small signal equivalent circuit would look something like this, GM VGS, right? And in that case, this is the source terminal of this MOSFET. And to simplify our analysis, we are neglecting the effect of R naught. That means we are considering R naught is, we are assuming R naught is very high, means close to infinity. So that way we can neglect the effect of R naught. Right? So we are doing that. Okay. Now see, if this is gate, if this is drain, and if this is source, then the current source, the dependent current source, the magnitude would be GM VGS, right? So here there is some term which is VGS, all right? So that means this is the gate terminal, this is the source terminal. So the VGS is basically this one, right? VGS is basically this one, right? Okay, isn't it? Now with this source, now we have connected another resistance which is RS. So with this source, we have connected one resistance which is RS, right? Okay. With this drain terminal, we have connected RD, and RD other terminal is grounded. We have RD, other terminal is grounded. And we have taken the output from this drain terminal, so the output is here. So output is expected to be plus here, minus here, right? Okay. Now, see this analysis here. Okay. Maybe we can
Sir,
take the, huh,
sir, can you please explain this RS part?
RS part. Like RS, which part, why we need RS, or from this circuit, how we are getting this circuit?
Sir, I mean to say that the junction, why is it not grounded?
Which junction?
Sir, that plus one.
Plus one. Which plus? Could you please?
S.
Yes, okay. So why do you think that it should be grounded? Because there is no capacitor now. If there was a capacitor, then for AC it would have been grounded, no?
Yes, sir. Okay, sir.
But now with source, this resistance RS is connected, so it would be connected like this only, no? Is
Okay,
it
sir.
clear? Is it clear to you?
Yes, sir.
Okay, okay, okay. Now, if this small signal equivalent circuit is right, then in that case, you see, this is the voltage VGS, which is dropping across this, between this and this. So if you take this as a, consider it as type of as a battery, and then you see the voltage drop between this point, right? Or maybe let me take another, this, between this and the voltage drop between this is VGS plus the drop across this RS, right? And through RS, this VGS, this amount of current should flow, right? This current has to flow through RS only. Then the voltage drop between this and this would be equal to this plus the drop across this RS, right? So if it is clear to you, let us write the total drop here. So it is VGS plus GM VGS into RS, right? So this is the total drop. And see, this is the total drop. So this should be the same as this drop, right? This drop, this they are in parallel. So the voltage should be same across this two, right?
Sir,
Now, oh, huh,
sir, why the current, all the current will flow through RS only?
because there is no path, no? See, where this is not connected, this source is floating, right? Here also this there is no path, no? So if there is no path, then the this current has to be equal to this current, right?
Okay, sir.
Okay. So it is GM VGS equal to this. So this voltage drop total would be equal to the voltage drop across. So this is equal to the voltage drop across R1 parallel R2, right? Which is nothing but this VI into R1 parallel R2 by R1 parallel R2 plus RI, right? The simple voltage division. So let me rewrite this expression as a whole here, right? So you can write this, okay? Now you can see here there are two VGS terms. So let me write it like in this way. This into 1 plus GM RS, that would be equal to VI into R1 parallel R2, right? Okay. Then we can write, so just finally write this expression as VGS expression as GM RS into R1 parallel R2, right? The same thing. Okay. Now, what will be the magnitude of this V out? So again, this current only has to flow through this RD, and when this current would flow, it will create a voltage drop in with this polarity plus here minus here, which is opposite to the polarity that we have considered. So the output voltage V output would be equal to minus GM VGS into RD, right? Voltage drop across this. Okay. Now we already know the value of or the expression of VGS. So we can probably substitute it here. So GM VI by 1 plus GM RS R1 parallel R2 by R1 parallel R2 plus RI into RD, isn't it? Now to find the gain, we have to do this V output by V input. So if we do that, it would come GM. Just let me write it in this way. So it would come as GM into this RD, just a type of rearranging this thing, plus 1 plus GMRS, this term, right, into R1 parallel R2 by R1 parallel R2 plus RI, right? Okay. Now you compare this gain. Okay. So this is the gain or small signal gain when RS is present or the source resistance is present, right? Now you compare this gain with the gain that we have find here. So this was the gain without RS. Let me copy it here so that we can compare side by side. So this was without RS, and this is with RS, right? So if you now compare this to this gain, then obviously you can see this term and this term, they are same, right? Here this GMRD, and also this minus term is same, right? But the additional term which you can see here, this is 1 plus GMRS, right? So the whole means the gain that you are achieving for without RS, that gain has to be divided by 1 plus GMRS. So obviously the gain reduces, right? For this gain, the gain reduces by 1 by 1 plus GMRS factor, isn't it? So the same thing we have also seen for CE amplifier. When we connect to one emitter resistance, we have seen that the gain will, small signal gain will fall, right? The same thing is also here. Now we can do one small approximation here, like the similar thing that we have also done for bipolar junction transistor. So that way, see, okay, let me write the assumption first. So if R1 parallel R2, this is much greater than Ri, right? So this is much greater than Ri, then you can probably neglect this. Then in the numerator we have R1 parallel R2, denominator we have R1 parallel R2. So that way this term become 1, right? So it has been oh sorry, not we are, this is without RS, right? We are not doing this here. So we should consider for this one. This one. So you see the same thing is obviously here. So it is R1 parallel R2 is much higher than this Ri. So this is much higher than Ri. So obviously then this term can be considered to be as 1, right? Okay. So that is done. Okay. Then, and if we assume that this GMRS, this term, if it is much greater than 1, then we can write this V output by V input is equal to minus GMRD by GMRS. So that way GM cancel. It becomes RD by RS, right? See, then in that way, I think I should put an approximate sign here. Then this small signal gain, okay, with RS, right? Small signal gain with RS can be reduced to this RD by RS, right? If you try to connect it with the previous whatever we have studied for bipolar junction transistor, there also we have seen the gain with when we have introduced one emitter resistance can be reduced to minus this RC by RE, right? The same thing you can also see from here, right? That the gain for this MOSFET for this type of configuration can be approximated to minus RD by RS. And obviously, when from here we have seen that without compared to the biasing where this RS was not there, but if the RS is there, there is a drastic reduction in the small signal gain. Now, to avoid that, what can be done? To avoid that, you know what you have to do. That is, you have to use probably one capacitor, right? You have to use one capacitor which is CS across this. So what this capacitor will do for DC stability, this capacitor is can be considered as an open circuit. So that way RS is present during the DC analysis, but even during the AC analysis, CS would be grounded. So that way the effect of RS is not be encountered in considering the small signal gain. So that way the gain would be much higher, right?
Sir,
Huh.
sir,
Hmm.
what might be the complication if we not ignore the early effect?
What will be the complications if we do not include the early effect?
Sir, if we, yes, sir, if we include the early effect.
Oh, if we include the early effect, it will, obviously you have then one more resistance here, and you have to do this entire analysis bit more carefully. Means this entire the analysis procedure would be same, but you will have little bit more number of terms here, which you have to take care.
Sir, that one resistance would be parallel to RD, right?
That one resistance would be parallel, but it's not actually completely parallel because you see here, because this small signal resistance, okay, this, okay, maybe from the previous one, let me show you here. See, this small signal resistance is between this drain terminal and source terminal. So if the source terminal is grounded, then it is fine that it is between drain and ground. But if the source terminal is not grounded, then you have to connect it between this drain and source terminal only. So for example, okay, like for this case, when you do not have any resistance here, right? So here you can see R naught is in parallel with RD, right? RD is another terminal is also grounded. For R naught, another terminal is also grounded. However, for this case, you see this for RD, another terminal is grounded, right? But for RS, right? No, for R naught, another terminal is not grounded because source is not grounded. So if you want to consider it, it would be somewhat like this. So R naught would be connected with the source terminal, not other terminal should not be grounded. So that way you cannot say they are exactly parallel. R naught and RD are exactly parallel. So that way your analysis would become a bit more like these equations would become bit more complicated. That's all.
Okay, sir.
Okay, thank you. Right. So this is the thing that was pending, and I think we have completed it. Okay. Now this is a bit type of maybe a new thing to all of you. So this is called enhancement load. Okay. So typically in our previous analysis, what we have seen that we generally use, like suppose if you have to use as an amplifier. So this is the, VDD supply. You take another transistor, apply this, properly bias this gate, and then apply the small signal here. And we connect one resistor here and take an output from here. Everything is fine, right? That's what we are doing here. So we can say that then this is basically RD, right? That's all we are doing so far. But now to implement this resistance, right, in IC, it takes some more space. Like space means real estate, right? On silicon chip, on top of that, it needs more space, right? So it would be better if we can replace or eliminate this direct resistance and replace this resistance by some active device. For example, it would be nice if we can also replace this resistance by a transistor, because to make the transistor we need very small space compared to that of a resistor. So that's what another thing has been proposed, which is just replace this RD with a transistor whose gate and drain terminal is shorted. So you can see from here, right? So here this particular transistor is not doing any amplification, right? But it is actually the load. Load means the resistance. Okay, so here actually it is the load, right? This is the RD is the load. So actually it is basically acting as a load, right? Right. But these are active devices. Transistors we are using as an transistor active device. This is passive device. And this type of load is called the enhancement load. So now think about it. Like then how can we do it, right? How can we just replace replace one resistor with transistor with gate and drain terminal shorted, right? Let us see the characteristics. Okay, how it will differ. Before that, let us see what would be the characteristics of this resistance. Say like we take one resistance, right? And try to measure the current or measure the current here, and you apply different voltage and try to measure the current, right? We are doing here voltage and current, right? So for resistance, okay, this IV characteristics would be like this only, right? I versus straight line, Ohm's law, right? And this is visible 0. Okay, now see the same thing what would happen for this particular type of configuration. So here our configuration is like this. Drain gate is connected, source is like this, right? And so basically see this for this resistance was two terminal device, and particularly this, if you internally connect these two, then also it becomes two terminal only, right? It has only this two terminal, right? Now here too you say like we will measure the current and we will like vary this voltage across this. right? So what would be the expected characteristics, IV characteristics, okay, for this device? Okay. Now see, for this gate and drain is connected. You know that when this drain and gate would be connected, the transistor would be always in saturation, right? Because here this VGS is equal to VDS, right? Which is much, which should be, which it is obvious then VDS is greater than VDS SAT, right? Because VDS SAT is equal to VGS minus VTS. Right. So from VGS, you are substituting something. So that is that will give you the value of VDS. And as this VGS is equal to VDS, then it is quite obvious that VDS is should be here greater than this VDS sat. So that way the transistor would be always in saturation. So once the transistor is in saturation, so we know the current voltage characteristics of this transistor is related by this equation VGS minus VTN square, right? Okay. Now this is VGS. This is gate to source voltage. Now gate to source voltage is equal to drain to source voltage here, right? So it is Kn VDS minus VTN square, right? So you see here, this is the I and this is the voltage, this V, right? Because this voltage V is applied across this DS. V is equal to this drain and source, right? So that way, now it is quite easy to plot the characteristics of this configuration. So you see, until and unless the applied voltage, that is V, or which is now VDS, is equal to VTN, then there is no current, right? So say that this is this VTN or the threshold voltage, then there is no current because you know the transistor operation, right? Until and unless it will cross, there will be no drain current. Okay. So once it cross, then it will follow this square characteristics, right? VGS minus VTN, that square characteristic. So that means the characteristics would look something like this, isn't it? So that way, you see, this particular configuration will give an IV characteristics like this, and this resistor would give an IV characteristics like this. Right? So from here, it is you can think that this transistor can also behave quite not exactly here should be straight line, but here it is a parabolic, but it is still showing this type of two terminal characteristics, device characteristics, which is not that way very far from this weight characteristics, right? The advantage is that everywhere we can replace any resistor by an um, transistor. So that way we can like the density of devices we can increase a lot. Okay. So is this enhancement load is clear to you?
Yes, sir.
Yes, sir.
Okay. Now see then, if you then suppose if you are using this enhancement load to make and or design an amplifier, right? Then you have to do the AC analysis of that. And for AC analysis, you have to also then substitute its equivalent circuit there, right? So for that, let us think that what would be the AC equivalent circuit for this, right? Or maybe should I draw it here? One second. Okay, let me draw it. So drain, gate, source, right? Okay. So this is the basic small signal equivalent circuit of any transistor, right? Of any this MOSFET, right? And here this is the drain, this is the gate, and this is the source terminal, right? Okay. But here we can clearly see this gate and source, they are connected. Gate and drain is connected. So that way we can connect this to gate and drain is connected. So that way you can see here VGS is means this terminal is now connected with this. Okay. Now you consider this is voltage VGS, right? And they are in parallel. So this voltage is also VGS, right? This voltage VGS, they are in parallel. So this voltage, because you can also assume that this is shorted. Same thing. Instead of putting it here, I could have also shorted it like this, right? So then this is VGS, then I mean this is VGS. So see the current source which is producing a current right, which is equal to Gm VGS and is producing a voltage across it which is VGS. Then what is the equivalent resistance of this? The equivalent resistance would be this R would be equal to voltage by current, right? This VGS, this Gm, this VGS. So basically it is 1 by Gm, right? The equivalent resistance of this. So this can be now think of, you can think of it as an resistance of 1 by Gm, 1 by Gm. Now you have an output resistance already. So this output resistance is R naught. And here you have these two terminal, which is this drain and this source. Okay. You have these two terminal, which is drain and source. So that way, this would be the equivalent circuit or equivalent, equivalent representation of this enhancement load, right? Is it clear to you?
Sir, could you explain it once, sir?
Yes, sir. Could you please explain it once more?
Okay. So here we are connecting this because of this configuration. You see this gate and drain are connected. So we have connected this gate and drain, right? So instead I could have connected it here, like same thing, right? Instead of connecting it here, this is the same wire. So you could have thought of like this. So this is the voltage VGS. The same voltage is dropping across here, right? So for this current source, supply current is I and the voltage drop across is VGS. So what will be the equivalent resistance? Equivalent resistance is this VGS by Gm VGS, which is equal to 1 by Gm. So this overall, this total thing can be replaced by a resistance, which is with the value of 1 by Gm. And you already have an resistance, which is due to the output or the channel in modulation. This is R naught. This would be in parallel with this 1 by Gm resistance. And this is these two terminals, right? Drain and source terminal of this MOSFET. So you can see here, this is the drain terminal, this is the source terminal. Is it clear now?
Yes, sir.
Yes, sir.
Oh.
So we are replacing the current source with a resistance of value 1 by Gm, right? Okay, sir.
Right.
Sir,
Huh.
sir, but we should have to study the characteristic of the, I mean the lower one, right? This is the not the primary MOSFET.
We in the next page only we are doing it. Huh? So see it here.
Okay, sir.
Okay. So here is this NMOS amplifier, means we are using an N-channel amplifier with an enhancement load, right? So then first let us say that this is the load, right? Let us identify it, right? And this is the actual device which is doing the amplification, right? This is actually doing the amplification. This is the load, means we have replaced the top resistance or top resistor by this transistor, right? Okay. Now, if we have understood this, then the small signal equivalent circuit of this transistor device is like this: gate, drain, source, GM, VGS are not D. D stands for this device. D stands for device, L stands for this load, right? So this is a small signal equivalent circuit. We have done it so many times. Now, what else we have to do? Okay, so see here, this when you do the AC analysis, this voltage source would be grounded, so that way this is gone. So you have only connected with VI. So let us connect it here. So you have this VI here, right? Okay. So this would be equal to this VGS. So VGS is equal to VI for this particular case. Okay. Now this is GM, VGS are not defined. Now what would be the equivalent circuit? What would be the equivalent circuit of this? So in this last page, we have seen that this enhancement load can be replaced with 1 by Gm parallel with R naught, right? So we can probably draw it here, something like this: 1 by Gm parallel with R naught, right? You see, this is VDD. So VDD would be grounded in small signal, right? and this terminal, the source, right, this terminal is now shorted with this source terminal is now connected with this drain, right, S and D. So this is now connected with this drain, isn't it? So this would be the equivalent circuit of this enhancement, means of this amplifier. Now the thing is that why to take so much paint and to draw it like this? We could have drawn this thing. We could have drawn this thing here only, na? GM and it is R naught. So let us write it R naught L and GM L. Let us write it here GM L and R naught L to identify that this is actually the part of load, right? You see the same. This is the
Sir,
same.
1 by GMS.
Right. It would be 1 by GML. Right. Right. So 1 by GML and R naught, right? It's the same thing, right? We have connected it. You could have drawn it like this, or you could have drawn it in this fashion, right? The same way. So that way, this part we can, right? No need to draw it. Show it, right? Okay. So here the output voltage is this one, right? So what would be the gain for this case? So for this case, you know, this VGS would be equal to VI. It's quite straightforward. So what is V output? V output is equal to minus GM VGS. This is the current, right? And this current is flowing through all this equivalent resistance. Means all this means equivalent of these three parallel resistances. So what will be the parallel combination? Just take the parallel R naught D parallel with 1 by GML parallel with R naught L, right? So it is V out equal to GM VI R naught D parallel with GML parallel with R naught L. So here the gain would be equal to V output by V input equal to minus GM R naught D, right? So this would be the gain for this type of NMOS amplifier with enhancement load. So it is not difficult. You can like if then in circuit enhancement load type of load is given, you should be able to find its right its gain, small signal equivalent gain.
Sir,
Huh.
sir, which means the only thing that we have to do is just to replace the resistance with these two parallel combination, right?
Yes, yes. Instead, like if you had suppose earlier here RD, right? Now that RD would be, I mean, for this type of configuration, RD would be replaced by these two parallel resistor, one by GML and R naught L.
Okay, sir.
Okay. Okay then. If you, it's already like taking 10:56. So if you do not have any question, maybe then we can stop here. And hello, do you have any question?
Could you
Sir,
please
in
tell
the
that how
small
to convert
signal,
the GML?
Huh. Yeah, in the small signal.
sir, in the small signal circuit,
Huh.
if we connect the G and S with a resistance, then will its behavior become similar to that of a BJT?
Okay. So you were saying that if we, what will happen if we connect this gate and source?
Yes, sir.
Okay. But okay. So what is that generally? Okay.
Sir,
What is
with a
the threshold?
resistance.
Huh.
Sir, with a resistance, I mean, I'm trying to simulate an RPi that was in a BJT.
Okay. You have also a resistance between these two, like this. Is it
Yes,
like
sir.
this? Okay. And how are you connecting this gate? Means this gate is connected with what? Voltage divider?
Sir, it may be connected in any way, but
No,
Uh,
that depends, na. That depends how you're connecting this, because that will determine, like, if you are, suppose if you have make it grounded, right? Then some current will, then the analysis will be one way. If you have not connected it to ground some other way, then the analysis would be another way, right? Because this will determine, right? The current flow through this resistance will determine what would be the voltage drop, means what would be the VGS.
okay, sir. So it will be dependent on the configuration.
Right, because earlier what you told, like if you suppose directly connect, then it would not work, because the threshold voltage is here greater than, means some positive value, right? For this NMOS. For PMOS, threshold voltage is
Yes.
negative. So if the threshold voltage is positive, now if you have connected, means this, that means VGS is equal to 0, right? So which is lower than the threshold voltage. So the transistor would be off only in that case.
Okay, sir. Sir, but why won't this resistance be similar to that of the R pi in a BJT?
Why this resistance? Which resistance you are trying to correlate with R pi?
The resistance we just introduced between G and S.
Between G and S. Right, this is the DC biasing resistance, and the R pi was the small signal equivalent circuit for BJT. So we do not connect R pi separately there. R pi is coming from the BJT only inside. Here, if you are connecting some resistance that is outside of this is the external resistance. This is not a part of this MOSFET.
Okay, sir. So in BJT, the DC analysis, the R pi, the internal R pi wasn't playing any effect, but here
No,
the
we have
RX.
not. We have never considered R pi in during DC analysis.
Yes, sir. Yes, sir.
Right, R pi only comes when we are doing the AC analysis, isn't it?
Yes, sir. Yes, sir. Got it, sir.
Okay, okay. Then I think your it's already time for your next class. Will be starting. Okay. So before we end, I would like to wish all of you a happy Durga Puja. Right. So enjoy your this holidays. Right. So we will again meet on next Monday. Right.
Same to you, sir.
Sir, happy Durga Puja, sir.
Yeah. Thank you.
Thank you.
Thank you very much.
Thank you, sir, and same to you.
Thank you.
Thank you.